This is a tutorial on how to make a solar system simulation using the Python library Pyglet. It starts from the very basics, such as creating a window and importing the necessary libraries, and gradually builds up to a fully functional and interactive solar system model. Throughout the tutorial, we add features like assigning planet specifications, creating orbital motion, adjusting lighting to simulate sunlight, and drawing each planet with realistic colors and sizes. We also introduce user controls such as zooming and pausing, which make the simulation more engaging and interactive. Each step is explained in a simple, easy to follow way, so that even beginners can understand the coding process without feeling overwhelmed. By the end of the tutorial, we read temporary random values with real astronomical data to improve accuracy and realism. The aim of this project is not only to teach coding techniques using Pyglet, but also to provide a deeper understanding of how our solar system functions. This hands-on learning experience makes it enjoyable and educational for anyone interested in programming or space science. We are developing a solar system simulation using Pyglet, a Python library designed for creating games and multimedia applications. Pyglet provides powerful tools for handling graphics, windowing, and user input, making it ideal for visualizing celestial bodies and their orbits in a dynamic, interactive way. In this simulation, we aim to represent the sun and planets, simulating their movement and scale to provide an educational and visually engaging experience. We are importing the required libraries, which is an essential step in setting up our solar system simulation. These libraries provide the necessary functionality for tasks such as rendering graphics, managing windows, handling events, and performing mathematical calculations. By including these dependencies at the beginning of our code, we ensure that all the tools and resources needed for the simulation, like drawing shapes, updating positions, and capturing user input, are available and ready to use. Due to some limitations of my computer, I am performing an additional step in the setup process that may not be necessary for others. This adjustment helps to ensure smooth execution and compatibility on my system, but it is specific to my environment. Therefore, you may not need to follow this step unless you encounter similar issues or constraints. We are now going to write the code to create a window for our solar system simulation. This window will serve as the main display area where all the planets, the sun, and their movements will be visualized. Using Pyglet windowing system, we can define the window size, title, and behavior, which forms the foundational stage for rendering our solar system and handling user interactions. In the next step, we are writing code to define the specifications of the planets for our solar system simulation. This involves giving each planet a name to identify it clearly, a size to represent its scale in comparison to others, a speed to determine how fast it moves around the sun, and a distance to place it correctly within the orbital layout. These values help us create a more accurate and engaging model of the solar system. By assigning unique characteristics to each planet, we can simulate their motion and appearance in a way that enhances the learning experience and makes the visualization more realistic. This structure also allows us to update or extend the simulation easily if we want to add more celestial bodies or introduce additional behaviors in the future. At this stage, I am using randomly assigned specifications for the planets, such as size, speed, and distance from the Sun. These are not actual or scientifically calculated values, but are chosen to simplify and speed up the coding process. This approach allows us to focus on building the structure and functionality of the simulation without getting slowed down by complex data. Once the simulation is fully developed and tested, we will replace these placeholder values with accurate and calculated planetary data to ensure the final visualization is realistic and informative. This step-by-step method helps to maintain progress while still aiming for a precise outcome in the end. Choosing colors for the planets is another important step because it adds to the realistic look and overall visual appeal of our simulation. Each planet in the solar system has a distinct appearance that helps us recognize and differentiate it from the others. To make this process easier and more accurate, I am using artificial intelligence to assist in selecting appropriate colors that closely resemble the actual visuals of the planets. This not only saves time, but also ensures that the simulation becomes more engaging and informative for the viewer. By giving attention to such details, we improve the quality and effectiveness of our visualization. Adding similar specifications for the Sun is also important because it is the central and most significant body in our solar system simulation. Just like the planets, the Sun needs to have defined attributes such as size, position, and color to create a balanced and realistic visualization. The Sun serves as the anchor around which all the planets orbit, so its accurate placement and appearance are essential for the overall structure and function of the simulation. Including these details helps enhance the clarity and educational value of the project while making the visual experience more complete and immersive. Giving values for the orbital angle of our solar system is an important step in coding the simulation. The orbital angle determines the position of each planet along its orbit at any given time. By assigning initial values to these angles, we can control the starting point of each planet's movement around the Sun. This allows us to simulate the motion of the planets and create a dynamic, realistic orbital system. As the simulation progresses, these angles will continuously update to reflect the planet orbits, making the movement appear smooth and lifelike. Now it is time to code for the angular or spherical motion of our solar system. This involves calculating and updating the positions of the planets based on their orbital angles, which are crucial for simulating their movement around the Sun. To achieve this, we will define the central data values, such as the orbital radius, speed, and angular velocity for each planet. These values will control how each planet moves in its orbit. We are now going to draw sphere shapes for the planets, which will give the simulation a more realistic look. Using sphere-like shapes for each planet enhances the visual representation, making it easier to distinguish between the planets and providing a more immersive experience. This step involves drawing circles or sphere-like shapes to represent the planets, ensuring their size and color align with the characteristics defined earlier. Although the planets in the simulation are being drawn on a plane, representing them as spheres will give the illusion of depth and make their movement more lifelike as they orbit the Sun. We need to adjust the light characters in space to enhance the visual quality of our solar system simulation. Space is naturally dark, but adding subtle light effects can help highlight the planets and the Sun, making them stand out more clearly. This can be done by simulating the glow of the Sun and how its light reflects on nearby planets. Light adjustment also helps create a sense of depth and positioning, giving a more three-dimensional feel to the simulation. By carefully placing and controlling these light effects, we improve the overall appearance and realism of the solar system while keeping the dark background of space intact to maintain contrast and clarity. we hope to follow an easy approach that is simple to understand and implement. By writing the central numerical values directly in the code, we ensure that the simulation behaves as expected and responds accurately during execution. These values include key elements such as light position, diffusion, specular, and ambient heat data values. Including them clearly in the code not only makes the logic more transparent, but also allows easy adjustments when fine-tuning the simulation. This step is important because these values directly affect the visual motion and arrangement of the planets, and any change in them will influence how realistic and smooth the final simulation appears. Sunlight emission is an important feature in our solar system simulation as it adds a realistic effect to the visualization. The sun is the central source of light, and simulating its light emission helps to create the impression that it is illuminating the surrounding space and the planets that orbit around it. This can be done by adding a soft glow or radiant effect around the sun, which gives the sense that light is being spread outward. This also helps in highlighting the planets more clearly as they move, especially when combined with slight shading or brightness variations to indicate how the light touches each surface. As humans, we sometimes forget to write certain parts of the code while working on a project. This can lead to issues in how the simulation runs. Regularly checking and testing the code helps catch these mistakes early and keeps the project on track. Forgetting is a normal part of the coding process. Catching and correcting these omissions early saves time and improves the overall accuracy and quality of the final result. Now that we have already given the specifications of the sun, we are simply writing the code to draw it in our simulation. The sun will be placed in the center, given a larger size and a bright color to make it look realistic. This step uses the values we defined earlier, and the sun will appear as the central body around which all planets move. This makes the simulation complete and gives a clear starting point for the movement of the rest of the solar system. Learning different projects with coding requires both time and presence of mind. Each project comes with its own set of challenges and new concepts that take effort to understand. It is important to stay focused and patient while learning, as rushing through can lead to confusion and mistakes. With regular practice and clear thinking, we can improve our understanding and handle more complex tasks step by step. Giving proper time and attention helps build strong coding skills and makes it easier to complete projects successfully. After completing the code for the sun, we are now going to code for the planets as well. Each planet will be given its own set of specifications, such as name, size, distance from the sun, speed of orbit, and color. These values help us to create a separate identity for each planet and control how they move around the sun. By using these details, we can write code that draws the planets and allows them to orbit in circular paths. This step brings more life to the simulation, shows how different planets move at different speeds and distances within the solar system. You can only truly learn coding when you have passion and an interest in exploring different projects. Coding becomes much more enjoyable and rewarding when you are genuinely curious about solving problems and building something new. Having a passion for learning keeps you motivated even when you face challenges. By working on diverse projects, you expand your skills and understanding, and each project becomes an opportunity to learn something valuable. The more you experiment and create, the better you become at coding, making it a fun and continuous learning journey. Coding each part separately is a great way to make the process easier and more manageable. When you break down a project into smaller sections, like coding for the sun, planets, or orbital movement individually, it allows you to focus on one thing at a time. This approach makes debugging simpler and helps you to identify fix issues quickly. Additionally, it provides flexibility. If you need to change or adjust something later, you can do so without affecting the entire project. This modular approach makes the final assembly of the project much easier, as each part works independently before being integrated. Things in coding may seem different and unique at first, but with regular practice, you become familiar with them. Over time, the more you work with certain libraries or functions, the more comfortable you get in using them efficiently. In the current code, we are simply utilizing the features provided by the imported libraries. These libraries offer predefined functions and methods that make coding easier, and as you continue to practice, you will become more adept at applying these tools to build your projects. Familiarity with these features will eventually make the process of coding feel more intuitive and seamless. In Pyglet, the draw function is used to show things on the screen. It is responsible for displaying the shapes, colors, and positions of objects like the sun and planets. Whenever we want to visualize something in our simulation, we place that code inside the draw function. This function runs every time the screen is refreshed, making it possible to update the position or appearance of objects smoothly. Using the draw function properly is important because it controls what the user sees and keeps the simulation active and responsive. Open is used at the beginning of our simulation to manage how objects are drawn and displayed. It gives us control over shapes, movement, and color to help build a realistic solar system. Even though the method may appear complex, it allows us to create smooth and detailed visuals entirely through code. This means we do not need to use any images, yet we can still show glowing effects, spinning motion, and orbiting planets in a way that looks natural. With practice, this approach becomes easier to understand and gives us more freedom to customize every part of the simulation. All the basic settings have been completed, and now it is time. See our simulation in action. We have defined the key elements like the sun, planets, their motion, colors, and overall display structure. Mistakes and errors are a natural part of the coding journey. They may seem frustrating at first, but they play an important role in helping you learn and grow. Each error gives you a chance to look closely at your code, understand what went wrong, and find a better way to fix it. This process strengthens your coding skills and builds confidence in handling different situations. Instead of feeling discouraged, it is better to see the positive side of mistakes as they guide you towards writing cleaner and more effective code over time. Hope you will learn from my mistakes. Build a stronger foundation for yourself. Every failure teaches a lesson that success often does not. Mistakes show where improvement is needed and guide you towards better understanding. They help you become more careful, more focused, and more skilled with each step in coding and in learning. Failures shape your experience and prepare you for greater success ahead. With patience and effort, these small setbacks become the reasons behind your strong progress. there is always room to improve your mistakes and your results, no matter how experienced or skilled you become. Coding is not just about getting things to work, but also about refining how they work. When you take the time to look back at your code, you often discover parts that can be made cleaner, more efficient, or easier to understand. Even a project that runs perfectly may have areas where small changes could make a big difference in how it performs or how easy it is to maintain. Mistakes are not signs of failure, but steps that show you what needs more attention. They offer valuable lessons that help you avoid the same issues in future work. By working on both correcting your mistakes and improving your final results, you build stronger habits, deeper understanding of how coding really works. You can see the advantage of using numerical values and other code structures separately because it allows for greater flexibility and control. By keeping these values separate, we can easily adjust them without affecting other parts of the code, making the process much simpler. Now, as we move forward, we are just fine-tuning these numerical values to make our simulation perfect. Small adjustments to things like speed, size, or distance can have a significant impact on the overall look and feel of the simulation. This approach makes it easier to experiment and find the best settings that create realistic and smooth experience. It also saves time, as you can focus on specific details without having to rewrite larger portions of the code. I hope you like this approach as well. It's a practical and efficient way to build a simulation, allowing flexibility and easy adjustments. By separating the different elements and focusing on refining specific values, it not only makes the coding process smoother but also provides better control over the final result. This approach helps in creating a more polished and realistic simulation without unnecessary complexity, and it gives you the freedom to experiment and improve the project gradually. Now it's your opportunity to improve the simulation by focusing on key factors like speed, distance, and size. By fine-tuning these numerical values, you can achieve more realistic movements and scale for the planets and the sun. Adjusting the speed will ensure that planets orbit at the right pace, while modifying the distances will give the correct spacing between objects. By tweaking the size values, you can make each planet appear proportionate relative to the sun and other planets. As here what I made by adjusting the size and distance values significantly improve the simulation. By increasing the size of the sun and planets, they appear more proportional, and modifying the distances between them creates more accurate orbits. These changes make the simulation look more realistic with better scale and visual appeal. it's time to add more functions to our simulation, starting with the zooming function. This feature will allow users to zoom in and out to get a closer or wider view of the solar system by implementing zoom controls, such as using the keyboard or mouse scroll. We can offer a more interactive experience. This will make it easier for users to explore the simulation and observe details like the orbits of the planets and the sun's position from different perspectives. Adding this function enhances user engagement and allows for a more dynamic, customizable view of the solar system. We are writing code for the zooming function using keyboard keys. The up and down arrow keys will control the zoom level, allowing users to adjust their view of the simulation. This function gives users the ability to zoom in or out, providing a more interactive experience as they explore the solar system. By handling key presses, we can modify the camera's perspective, making it easier to observe different parts of the simulation from varying distances. Encoding, practice and playing with your code is the best way to learn. Experimenting with different values, functions, and features helps you to understand how everything works and how small changes can have a big impact. The more you interact with your code, the better you get at identifying issues and finding solutions. This hands-on approach teaches you in a way that no textbook or tutorial can, as it allows you to learn through trial and error, gaining real insight and building confidence in your abilities. We are now going to add another keyboard key button to pause the simulation, but with a unique approach. Rather than pausing the entire motion of the solar system, we will focus on pausing only the sun's movement. This means that the planets will continue their orbits, but the sun will remain stationary. The reason behind this decision is to give users the opportunity to observe the planets in motion without the distraction of the sun moving as well. It provides a fresh perspective, allowing users to focus on the dynamics of the planetary orbits while still maintaining the overall flow of the simulation. This selective pausing feature adds a layer of interactivity that enhances the user experience, offering more control over the simulation without disrupting the movement of the entire system. It's a small but effective change that adds a new dimension to exploring the solar system in our simulation. We are going to use the spacebar button to pause the sun's motion in the simulation. The spacebar is a commonly used key for triggering actions in many applications, making it a natural choice for this feature. When pressed, the spacebar will stop the sun from moving while allowing the planets to continue orbiting. This offers users a simple way to interact with the simulation, giving them control over specific elements without interrupting the entire system's dynamics. It's an intuitive and efficient way to enhance the interactivity of the simulation, making it more engaging for users. I forgot something to write in the code, and it's a common occurrence during development. Sometimes it's easy to overlook a small detail, but these missing words can make a big difference in how the code functions. We are adding another feature to show the angular orbital lines, the planet's pathway, which will visually represent the path on which each planet moves. These orbital lines will give users a clearer understanding of the planet's orbits around the sun, adding a new level of interactivity to the simulation. By displaying these lines, it becomes easier to observe how the planets travel through space and maintain their orbits. This feature not only enhances the visualization of the solar system, but also helps in understanding the concept of orbital mechanics more effectively. All the basic level features have been set up, and now it is time to complete this tutorial by replacing the supposed values with real, calculated ones. Using actual data for size, distance, and speed will make the simulation more accurate and realistic. This final step brings everything together, turning a basic visual model into a more scientifically and correct representation of the solar system. It helps us better understand how each planet behaves in space and adds credibility to the overall simulation. Hope I made this tutorial easy to understand and follow. The goal is to explain each step in a simple and clear way so that anyone interested in coding could build and learn without confusion. By breaking down the process, using straightforward language, and adding features one by one, it becomes easier to grasp the logic behind the simulation. This method not only helps in learning how to code, but also deepens understanding of how the solar system works through visualization.